So let's start discussing, using quantum statistical mechanics for practical purposes. So the first thing I would like to do is show you how the third law of thermodynamics is actually a very simple consequence of the way we define everything, entropy, etc., etc. The moment we start using quantum statistical mechanics instead of classical statistical mechanics. And the reason is that in quantum statistical mechanics, essentially the most natural thing you have, if you have a closed system, is a spectrum that is discrete, right? And therefore, when you count the number of states that in a microcanonical shell at the minimum temperature, which corresponds, minimum energy, which corresponds to zero temperature, so close to the ground state, what happens is that you have a ground state which is separated by a gap to the excited states in a finite system, and that tells you that at low enough temperatures you will occupy only the ground state, and the microcanonical entropy is going to be zero. Unless you have a bunch of degenerate ground states, which might be the case in systems. Not only, when you have symmetry breaking, is trivial because you know that you will occupy only one of the many ground states that are connected by symmetry. For example, if you have spin up or spin down in an easy model, you will always be sitting in one of those two guys. In a real system, there are some more complicated systems that have so-called topological excitations in quantum mechanics that might end up having multiple ground states with multiple degeneracies. In that case, life is a bit more complicated. But let's forget about pathology. The normal most of the systems actually displays zero entropy at zero temperature. And to show you how this works, let me do the statistical mechanics of the simplest possible quantum system, which is the harmonic oscillator. You know how to diagonalize an harmonic oscillator, right? In terms of creation and annihilation operators. So I will not bother telling you the story. What is important for you to know is that if you know how to diagonalize an harmonic oscillator, a spin, which is a 2x2 matrix, and a level decaying in a continuum, you practically know everything in quantum mechanics, and all the rest is just a consequence. Because, well, most of the calculations just follow from these three examples. In any case, so we'll take this guy. Of course, I'll take h bar equal to 1. I'm not going to carry. And as you know, the eigenstates, which in the momentum representation, so position representation, are complicated Hermite polynomials, in this representation are just obtained by applying a dagger n times and normalizing by square root of n factorial. Acting on the vacuum is defined by the fact that A acting on the vacuum is equal to 0. All right? So let us now, knowing that these are the eigenstates, compute the partition function. All right, so the partition function is trace, by definition, the canonical partition function is trace of exponential of minus beta h. Okay? So, which is equal to
summing up with all and the sum of all.
Sum over all n's of
bra minus.
Well, let's do it slowly. So bra n e to the minus beta h n, and which is equal to sum over n, and then e to the minus beta
h bar omega n plus
h bar omega. H bar is equal to 1 omega. So n plus 1/2. Okay? Now you see that this is actually very, very simple because I take e to the minus beta omega over 2, and then I have sum over n running from 0 to plus infinity of e to the minus beta omega to the power n. And this is equal to what?
1 over the
1 over
1 plus e to the minus beta.
1 minus
1 minus.
e to the minus beta. Remember this. So if you have sum over n from 0 to plus infinity of r to the power n, this is equal to sum over 1 minus r, right? Of course, r should be smaller than 1, right? So here r is smaller than 1, and therefore we get e to the minus beta omega over 2 divided by 1 minus e to the minus beta omega. Okay? So this is my partition function. So now, once I have the partition function, the next thing I should do is
Take the log of it and
take the log of it. The partition function is not a physical quantity, right? So what you want is the free energy. So you take the log of it. So 1 over beta log of z. And if you take this log, you see that you get omega over 2 plus 1 over beta, the log of 1 minus e to the minus beta omega. Now, if this is your free energy, so let us compute some physical quantities and let's see what comes out and to understand a bit of the physics of this problem. And this is the simplest possible calculation in quantum statistical mechanics you can do apart from just a single particle, which is trivial. So let us compute, for example, the average energy, right? So if you compute the average energy, you have to take the derivative with respect to beta of the log of z. And if you do the calculation, which is straightforward, so I'll let you do all the derivatives, etc., you will get this result. Okay, so the average energy is omega over 2, which is just a 0-point energy, times omega times 1 over e to the beta omega minus 1, right? You could think of this, so you could think of this as omega over 2 plus omega times the average occupation, if you want, right? The average occupation of your, or the average number of quanta in your harmonic oscillator, and that tells you that this average of n is equal to 1 over e to the beta omega minus 1. We will see this appearing later on when we will be discussing bosons and fermions and so on and so forth. So this is the result we get. Now, notice one thing of this result. First of all, what happens if the temperature goes to 0?
if the temperature goes to 0, the oscillator is in the ground state?
No, that I know, but what happens in the formula? What is the average energy and the temperature? Omega over 2. And this is correct because, as you were saying, in the ground state, at 0 temperature, the oscillator is in the ground state, and therefore we do expect it to have an average energy which is equal to omega over 2. On the other hand, so if temperature goes to 0, average E tends to omega over 2. Now, if the temperature is instead very large, well, let's say that the temperature is much larger than omega, just to be precise. then what happens? What happens is that you can take this exponential here and expand it because the exponent is small. And if you expand it, you get omega divided by beta omega. So you get that average E is essentially omega over 2 plus omega divided by beta omega. So the 2 omega go, and since KBT is much larger than omega, this is essentially KBT, right? For large T. So this is what we expect from what? From the equipartition theorem. So you see two things that are important in this very, very simple analysis. First of all, in quantum mechanics, there is no equipartition theorem in principle, right? Because you see that the average energy, you cannot just state as in classical mechanics that the average energy of an harmonic oscillator is just KBT, right? In classical mechanics, that was a statement, a theorem. There's nothing you can do about it. Here, it's not true, okay? And this is, by the way it was discovered, one of the ways that quantum mechanics was discovered, as you all know. You know the story of the blackbody radiation, right? So blackbody radiation, it's a radiation that comes out of a blackbody, does not satisfy the equipartition theorem, and therefore, you're in trouble. You don't understand what is going on there until, Planck comes in and understands that the reason is that there are some quanta, etc., etc., etc. So, there is no equipartition, and equipartition is valid only when the temperature is much larger than the frequency. What is the frequency? The frequency is the gap in the spectrum of the harmonic oscillator. So when the temperature is much larger than the gap of the harmonic oscillator, then in practice the system behaves as classical. And that you know very well, because so how do you get that, for example, well, if you look at the time evolution of x and p in the harmonic oscillator, they always obey the classical equations of motion, right? But in practice, if you look at the probability distribution, right, the evolution of the probability distribution, when do you expect it to be really classical, so to have a nice probability distribution that behaves as a nice harmonic oscillator? Well, in practice, when the number of quanta you're exciting is very, very large, okay? When the number of quanta you're exciting is very, very large, in practice the system behaves kind of classically. And when the temperature is large, so that's essentially what you're doing. You see that when the temperature is large, the average occupation grows as KBT, right? Well, it grows as KBT divided by omega. So it grows as the ratio of T divided by omega, roughly. Okay? So we have high temperature, kind of classical systems, low temperature you start seeing quantum mechanics. We will see this in more detail later on. Now, another quantity we could compute is the entropy, S. So the entropy is the derivative with respect to temperature of the free energy. And if you take this derivative, you will get minus K Boltzmann log of 1 minus e to the minus beta omega plus omega over t. Well, here I'm putting in so sometimes I keep, sometimes I don't keep K Boltzmann. Let's not keep it. Just be consistent. 1 over e to the beta omega minus 1. Right. So now, let's look at this formula. What happens when beta omega is much larger than 1? So when the temperature tends to 0.
In that case, the logarithm goes to 0?
Yes. And also the other guy goes to 0.
Yeah.
Right? So everybody goes to 0. So in practice, when the temperature goes to 0, the entropy itself S tends to 0. Now, what happens now when beta omega is much smaller than 1? This is a bit more subtle. What? Yeah, you do a Taylor expansion of the exponential, right? And what do you get? So you will get minus s approximately minus logarithm of beta omega plus, well, from the other you do the expansion and you will get 1, so you will get 1, right? Considering that we took k Boltzmann equal to 1, right? So now this is equal to the log of t over omega plus 1, but t over omega is much larger than 1 anyway, so the log of t over omega is much larger than 1, and therefore this is just the log of t over omega. And now what I would like you to do is to give me a physical interpretation of this. What is t over omega for t much larger than omega? What?
Log t.
Well, say, yeah, it's log of t over omega. But what is the physical meaning of t over omega for t much larger than omega? We said it before. I just said it. You know, it's being recorded. I said it. You can go to the website.
This has to be entropy of classical oscillator, in some sense.
Well, it is, yes, and?
It will be log of t minus log of omega.
Yeah, well, that is correct, but then what is t over omega? What is the physical meaning of t over omega?
It's the excitation to the difference between the excitations.
You're close, say it a bit better. What is it? What did I say before? What is t over omega? How many quanta am exciting when I have a given temperature T much larger than omega? How many?
A lot.
Yeah, well, that's a good answer, right? A lot. Great. How much a lot? So let's do it, right? So if average n is equal to 1 over e to the beta omega minus 1, when t is much larger than omega, this is equal to what? This is approximately 1 over beta times omega, which is roughly, well, which is equal to t over omega. You see? T over omega is the number of quanta that I'm exciting. And my entropy is equal to the log of the number. Okay? Log of the number of quanta that I'm exciting, well, on average, in my system. Here? It's important to give a physical meaning to formulas, otherwise you don't understand what you're calculating, right? I mean, unless you're a mathematician, right? In that case, formulas are meaning by themselves. All right, so you see that, therefore, you know, what we extract from this simple exercise that in principle I could give you as a homework is that So at zero, I mean, the exact solution of this simple problem in statistical mechanics tells you that at low temperatures, you have the third principle of thermodynamics, the harmonic oscillators behaves very non-classically, etc., etc. But when you are at high temperatures, then you start seeing the effects of, then you don't see anything. You practically see your harmonic oscillators as behaving as a classical harmonic oscillator. Okay? So the basic Partition theorem, etc., etc., etc. Clear? All right. So there are many exercises you could do to see the difference between classical and quantum statistical mechanics. But they are different at a very fundamental level the moment you, for example, start solving the other simplest possible problem you can have in statistical mechanics, which is the study of the ideal gas. Okay? So let us now focus on quantum ideal gases. All right. So an ideal gas is a system which is described by this Hamiltonian. Of course, now our PI, our momentum operators, I'm not specifying the representation, it's not important. And as you know, I hope, when you have a gas of n identical particles in quantum mechanics, you have to worry about the symmetry of the wave function. You have done this in advanced quantum mechanics?
Not yet.
Not yet. Well, as you don't know, when you deal with a gas of what are you doing now in advanced quantum mechanics? What? Perturbation theory. Okay. Well, you will get there. Anyway, I'm telling you. If you have a gas of particles, or actually two particles, even two particles, it doesn't really matter. So you have to think, the entire wave function has to be symmetric under the exchange of indices, right? But then everything depends on whether your system is a system which is a so-called fermion, systems of fermions or of bosons. Whether something is a fermion or a boson depends on the total spin of the particle, right? So, for example, if your particle has spin 1/2 is a fermion, if your particle has spin 1 is a boson, and so on and so forth. And the difference between fermions and bosons is that, so for fermions, the spin component of the wave function is antisymmetric, and therefore the orbital component of the wave function has to be antisymmetric as well in order to compensate for the minus sign that you will pick up when you exchange particles in the spin component, right? If you have if you have bosons instead, the spin component is symmetric and therefore also the orbital component is symmetric, full stop. Now, what is the implication that is important for us? And then we will forget about symmetry of the wave function. The most important implication of being a boson or being a fermion, which is important for statistical mechanics, is the following. If you are a boson, if you are a fermion, and you have two particles who are fermions, they cannot live in the same state, right? And the reason they cannot live in the same state is essentially that if they would live in the same state, since the wave function has to be antisymmetric, then of course you get a contradiction, right? So two fermions have to necessarily live in different states. So the maximum occupation of a given level, spinless level for fermions is 1, and that's it. If you have bosons instead, then you can put as many particles in one level as you want. And that's it. So this is the only thing that is important for me for statistical mechanics, and that you have to remember. Then all the details of symmetrization of wave function, blah, 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 you will do them with Giuseppe Santoro and I think it was Ariel Fazius. Yeah, so you will do it with them. All right, so now, so now we have a gas of, what is going on? So we have a gas of particles now in a finite volume, and in particular, so if we look at the spectrum for a single particle, epsilon of p is going to be p squared over 2m, and I'm going to, well, I'm sure that you have seen it. I hope that you have seen it. Otherwise, I'm saying something that you haven't. But if you take a single particle in a box, right, and you put periodic boundary conditions, have you seen this? Right? Then you know that the momenta come out to be quantized in units of 2 pi over L. L is the size of the box. So if you have a one-dimensional box, it's going to be 2 pi over L. If you have a three-dimensional box, then Px is 2 pi over Lx, Py is 2 pi over Ly, Pz is 2 pi over Lz, and where n is an integer. Now, in particular, so therefore, whenever I will do calculations with this spectrum, I will end up summing over this discrete set of p's, right, which come out from this quantization. And one thing that you might have seen is that when you have this sum and you pass to the continuum limit of this sum, it's very easy to do that. It's just enough to put a v divided by h bar cube, no, h cube, not h bar cube, integral dt. Okay? So these are the rules of the game. Now, if we take now this problem, it's clear that the energy of this gas of particles is always going to be sum over p, epsilon p, and p, where the p's are selected according to this rule. You agree with me? And the total number of particles is going to be sum over p and p. And the only difference at this level between fermions and bosons is that Np is equal to 0 or 1 for fermions, or 0, 1, 2, and whatever you want for bosons. So these are the rules of the game. Now, given these rules of the game, let us now compute the grand canonical partition function. So z mu vt, which is equal to the sum for n from 0 plus infinity of Zn times Zn Bt, where Zn, the canonical partition function of n particles, is just equal to the sum over n e to the minus beta en, which in practice is equal to the sum over all possible configurations of my np's, I'm not specifying what they are, such that the sum over p and p is equal to n of e to the minus beta sum over p epsilon p and p. You agree? So this is the canonical partition function. I'm summing over all possible configurations of my particles. And what kind of configurations I will have depends on whether I will have bosons or fermions. I must have this constraint because I'm fixing the number of particles. And then I have e to the minus beta times the energy of that given configuration, which is given by this expression because of what I wrote before. Okay? Great. So now let us take this expression here and plug it into this formula. So we get that our rank canonical partition function is equal to the sum over n from 0 to plus infinity, the sum over np, sum over p, np equal to n of e to the minus beta, sum over p, epsilon p, np. And now what do I do?
We need to test 0 n.
We need to do what?
We forgot the z of n term.
Yes, you're right. You're right. So now, so we can write the z of n as follows actually. Let's write it explicitly. Z of n, I can write it as e to the beta mu sum over p and p. Right? Okay, so now what do I do with this expression? We have seen something similar to this in the last lecture.
We forgot about the constraint.
Sorry? We forget about the constraint, right? So you remember, we have done something, a similar sum when we talked about the cluster expansion. We were summing over all possible number of particles over all configurations of clusters such that the sum over, the sum over L and L was saturating the number of particles. So here we have something very, very similar. And what I want to say is that now we can write this as the sum over all possible configurations without constraints of e to the minus beta sum over p epsilon p minus mu times np. Right? You agree with me? I'm summing without putting any constraint. Great. So now, well, this sum over all constraints, if you think for a second, is equal to is equal to the, it's exactly the same calculation as for the for the cluster expansion in a sense. I mean, it's very, very similar. Here we write this as product over p e to the minus beta epsilon p minus mu np. And now we exchange product and sum as we have done for the cluster expansion, right? So we get that this is equal. So I see that all of you have redone the calculations of the cluster expansion because you're all familiar with this. So this is equal to product over p of the sum over np of e to the minus beta epsilon p minus mu np. And now you see that when I want to perform this sum and then take the product, now it's important to distinguish between bosons and fermions, because the extent to which, I mean, if I have bosons, I'm summing over only np equal to 0 or 1. If I have fermions, np is equal to 0 or 1. If I have bosons, it's equal to whatever I want. So let's do it first for fermions. So for fermions, you have that sum over n p e to the minus beta epsilon p minus mu np is equal, well, the sum over np equal to 0 or 1, so therefore this is equal to 1 plus e to the minus beta epsilon p minus mu. And that's it.
Sorry. The problem that we are discussing at this point, is it one-dimensional box or three-dimensional?
It doesn't matter. Doesn't really matter. Because I'm multiplying over p's, you see? I'm multiplying over p. So the p can be, you know, a three-dimensional vector, can be a two-dimensional vector, can be a one-dimensional number. Doesn't really matter, right? It's the quantum number that classifies my single particle states. Is that clear? It doesn't matter whether it's 3, 2, 1 dimension at this point. So if I have bosons instead, then what I have is sum over np from 0 to plus infinity of, again, well, e to the minus beta epsilon p minus mu to the power np. Now you see that I have the same story as the harmonic oscillator. So this is going to be 1 minus e to the minus beta epsilon p minus mu to the power minus 1. Okay? It's actually interesting. You see that there is a minus sign difference and a minus sign difference in the exponent and nothing else. But this minus sign difference has crucial physical effects. Okay? So it's not something trivial. So we will see later on what are the effects. So therefore, if we just finish this calculation, we end up having that our grand canonical partition function is equal to product over p of 1 plus e to the minus beta epsilon p minus mu for fermions, or z is equal to product over p of 1 minus e to the minus beta epsilon p minus mu to the power minus 1 for bosons. Okay?
If epsilon p is bigger than mu.
Yeah, that's a very important statement. If epsilon p is bigger than mu. Now, that tells you that in order for this to make sense, right? If you have bosons, the chemical potential, in order for this calculation to make sense, should be negative or at most 0. Right? Why? Because if it's positive, then for certain p's you would have a negative occupation, which doesn't make any sense. Clear? All right. So for bosons, for bosons, the chemical potential is negative or 0 at most. Now, as we will see in not this lecture, next lecture, actually fixing the chemical potential for bosons and playing the game of finding, given a number of particles, what is the chemical potential at different temperatures, will lead us to discover that for certain systems at certain temperatures you might have the phenomenon of Bose-Einstein condensation, which is the situation in which a macroscopic number of particles want all to sit in the same level, right? This doesn't happen for fermions. For fermions, the chemical potential, well, can be whatever you want. There is no divergence, and typically the chemical potential is fixing, fixing the density in such a way. I mean, at very low temperatures, is fixing where is the position of the Fermi energy, which is, well, okay. I don't know if you have done this in solid state physics, but maybe yes. So there is a Fermi sphere, Fermi energy in metal. Have you done this? Yeah, so you know this stuff. So it's fixing the position of the Fermi energy at low temperatures, not at any temperature. At any temperature is more complicated. All right, so when I see something trivial, you should tell me, yeah, professor, it's trivial, we know that, right? Okay, you should just tell me, yeah, of course, I mean, we know this. All right, so it's not the first time you see these distributions then? It's not, or it is?
Yeah, it is or yeah, it's
No, it's not.
It's not. Then I can move faster. No. Okay. All right. So, given this, now let's try to compute the average number of particles, right? So, in order to compute the number of particles, this is 1 over beta log of, sorry, not log, d mu of the log of z. And now, if you do the calculation, which is straightforward, so I'll let you do it. I mean, really, you just have to take derivatives. You will find that this is sum over p of 1 over e to the beta epsilon p minus 1 plus or minus 1. So we can interpret this as sum over p times the average occupation of the mode with momentum p, right? Or with energy epsilon p. And this tells us that n bar of p can have two forms. If you are dealing with fermions, it's a Fermi-Dirac distribution. If you're dealing with bosons, it's a Bose-Einstein distribution. Fermions and bosons. Now, the Fermi-Dirac distribution, even if you plot them, these two functions are completely different. Okay? Because the Fermi-Dirac distribution is a nice smooth function. It behaves like this. It's equal to 1 and then equal to 0 at large enough omegas, well, or p, epsilon p, let's say. And then it has a transition with a width, well, this is a bad drawing, but the width of this transition is kBt and it's centered around the chemical potential. Okay? So this is n Fermi-Dirac. You see, it's telling you essentially, for all energies that are well below the chemical potential, you fill up 1 fermion per level. For all energies that are well above chemical potential, you fill up 0 fermions per level, and in between you have a transition region in which the number of particles actually fluctuates. So the average occupation is smaller than 1, but if you would compute the fluctuations of the number of particles, right, so del and f, well, then you would see that these actually are peaking along this position here, right? For fermions, this is equal to np times 1 minus np. Well, I'll let you do the calculation. It's very simple. So this function here, you see that it's finite only if np is not equal to 0 nor 1. Okay? So if it's something in between, then it's finite. Otherwise, it's equal to 0. So it's going to be 0 here, and then the fluctuations are going to be maximal close to this point. Now, for bosons, the story is completely different. That's what makes bosons by far much more complicated than fermions. Fermions are much, much simpler than bosons. So, bosons have a certain chemical potential. So in principle, the distribution function is divergent as epsilon p gets equal to mu, but then you would have a function that looks like this, right? So you cannot have a negative occupation of a level. Right? I mean, I think it's obvious, right? You cannot put a negative number of particles in a level. Perhaps, maybe. I mean, I don't know. I find it obvious. So therefore, this tells you that the chemical potential should be sitting on this side, right? Or at most reach 0. And therefore, this function here is simply something that has a certain value here that in principle, if the chemical potential hits 0, is going to diverge. And then it's going smoothly to 0 as epsilon p goes to infinity, right? So this is equal to n Bose-Einstein of p. And the value here is actually e to the minus, just a second, blah, 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 is 1 over e to the minus beta mu minus 1. So you see that in order for it to be positive, the chemical potential has to be negative, right? Now, what is interesting of both distributions is that if you look at the tails of this distribution, when epsilon p is very, very large, then in both cases, and for epsilon p much larger than t, in both cases you get the same expression, e to the minus beta epsilon p minus mu. Right? When epsilon p is much, sorry, actually here to be precise should be epsilon p minus mu much larger than t. Then in both cases you end up having the same kind of factor, which is essentially a Boltzmann factor, right? You see, so it's classical. So this tells you again that in order to see the discrepancy between classical statistical mechanics and quantum mechanics, you should go to temperatures which are sufficiently low in order to see the quantum effects. If your temperature is so huge that in practice this distribution here is doing something like this. So, I mean, if kBt is much larger than epsilon p minus mu, so you see this width is getting to be much larger than this figure. You see that this figure here will look like this. This one will look pretty much the same. In both cases, you will have an exponential and you will not be able to distinguish between the two. So at very high temperatures, matter looks classical. It's only at low temperatures that it looks quantum mechanical. Okay? All right. So now let us continue. So now we're going to compute the equation of state for the ideal fermionic gas. But before doing that, you give me 2 minutes and I'll come back. Okay? So we stop for, stop unless you want to record yourself. Let's continue now with the ideal gas for fermions. All right, so in order to compute the equation of state for the ideal gas, well, we know what to do, right? We know what is the Courant canonical partition function, so we know also that PV is going to be equal to 1 over beta log of z. And at the same time, since z is going to be dependent on the chemical potential, as we have done previously, we should also, you remember the calculation for the cluster expansion. Also in this case, we should find the number of particles as a function of chemical potential and vice versa. So therefore, we should have we should compute also the number of particles, which in this case is trivially given by sum over p 1 over e to the beta epsilon p minus mu plus 1. And this log is nothing but sum over p, 1 over beta, sum over p of log of 1 plus e to the minus beta epsilon p minus mu. Okay? You all agree? Good. All right, so now let's pass. So the reason I told you about the passing to the continuum limit in from sums to integrals is that I want to do that right now. And in particular, I want to rewrite this as follows. So p v over kbt, I want to, so if I pass to the integral, is going to be equal to, so this sum over p is going to be v over h cubed. So it will give me v over h cubed times integral dp. Now it's important to specify whether I'm in 2, 3 dimensions, 1 dimension, or whatever. Because if I really want to perform this integral, epsilon p is always the same, it's p squared over 2m. So now everything depends on whether I'm in 2 dimensions, 1 dimension, or 3 dimensions to do the integral in spherical coordinates. So let's say we are in 3 dimensions. So if we're in 3 dimensions, the integral is going to be dp 4 pi p squared times the log of 1 plus e to the minus beta, and then you have p squared over 2m minus mu. Now, same thing for n. I'm going to have that this is v over h cubed integral dp 4 pi p squared of 1 over e to the beta p squared over 2m minus mu minus 1 plus 1. Okay? Great. So now you see something peculiar. You see that in these integrals I always have a p squared over 2m multiplied by beta, and then a p squared sitting here. So I could change variables in both of them, and I could set x squared equal to p squared over 2m times kbt, or beta times p squared over 2m. Now, if I do so, then, and I remember that z is equal to e to the beta mu, so in practice what stays written here, I can see it as z times e to the minus beta p squared over 2m, you see? And same thing down here. This is z times e to the beta p squared over 2m. So now I can rewrite this as follows. So let me first write the formula, and then I'll explain what I mean. I can write this as p over kbt equal to 1 over lambda cubed times some function f of z, where lambda is the thermal wavelength, so it's square root of 2 pi over n k bolts on t, And what is fz? Fz is the function 4 over square root of pi integral between 0 and plus infinity dx x squared log of 1 plus z e to the minus x squared. So, what I did here, if you compare it to what I had before, is nothing special. I just made this change of variables. This change of variables will spit out a combination of 2m kbt in front of the integral. I'll combine it with the h cubed to give me this. By the way, there is an h missing here. Where the hell is the h? Should be up. H, just a second, h cubed, so it should be an h squared. Right. So I combine the h with what is spat out by the integral with this stuff to obtain this wavelength here, which is just a global prefactor to the cube, and then the integral that is left behind as this form, where z is the fugacity. Okay? And now I have to calculate this integral. And it looks very scary, but it's not scary at all. Because one thing you can do when you see this integral is you can expand it. You can expand this function in powers of this, in a Taylor series of this second argument, right? So you can write this as 4 over square root of pi integral between 0 and plus infinity dx, and then you will have x squared, and then you will have z e to the minus x squared minus z squared over 2 e to the minus 2x squared plus z cubed over 3 e to the minus 3 times x squared plus etc. etc. And now what I can do is, you see here I have integral dx x squared e to the minus x squared. Here I have integral dx e to the minus 2x squared. But these two can be absorbed into x by just making a change of variables, and I will just spit out a constant. In other words, this can be rewritten as 4 over square root of pi integral between 0 and plus infinity dx x squared of z e to the minus x squared sorry, yeah, it's okay, minus z squared over 2 to the power 5 halves plus z cubed over 3 to the power 5 halves minus etc. etc. times e to the minus x squared. Now all these coefficients, if you go through the calculations, just come out by making the change of variables. Okay? And the factor of 5 halves comes from the fact that you will have to put in here a square root of 2, so 1/2, and then you will have here a factor of 5, so you have 5 halves sitting downstairs. So if you do the calculation carefully, you will see that it comes out. All right, so now we're practically done, because this is equal to what? Is equal to 4 over square root of pi. Then I have z minus z squared over 2 to the power 5 halves plus z cubed over 3 to the power 5 halves minus etc. etc. integral 0 plus infinity dx x squared e to the minus x squared. This is just a Gaussian integral. I know how to do it. I don't remember what comes out at the moment, but it essentially cancels out the 4 over square root of pi in front, and therefore you get at the end that the result of your integral is sum over L from 1 to plus infinity z to the L minus 1 to the power L plus 1 divided by L to the power 5/2. Full stop. So therefore, what we get is finally that our P over kBt is equal to the sum over L from 1 to plus infinity minus 1 to the power L plus 1 ZL divided by L to the 5/2 times lambda cubed. And now I have to find a similar expression for n. And it turns out that for n, you will find that n over v is equal to sum over L. If you repeat the same calculation and you expand 1 over 1 minus e to the minus beta omega, so you will get this. And that's it. Now, given these two formulas, then you can essentially close at all temperatures the equation. I mean, you can find the chemical potential as a function of n or of the density, and you can plug it in here and find P over kBt as a function of the density. So this is the equation of state for fermions. Now, what you should expect is that if I never did this calculation, let me see. Yeah. If I see it directly from here, but I'll let you check it yourself. You should see that if the temperature is much larger than epsilon p minus mu for all p's, right? Which might be hard, you might have to put a cutoff, right? But it's okay. If the temperature is super huge, in such a way that you can expand out to this exponential, because it's essentially always much smaller than 1, then you see that here you have P times V times is equal to 1 over beta sum over P e to the minus beta epsilon P minus mu, right? If you can expand out this exponential. But n is equal to the sum over P of e to the minus beta epsilon P minus mu in that limit. And therefore we see from this that in the classical limit, we do get the equation of state for the ideal gas. You see it? But in general, this is different. So you're not going to get P times V equal to nk Boltzmann T, right? For fermions, only in the classical limit. And it works out nicely. All right, so now, before moving to bosons, which we're not going to manage to do it today, but what is going to happen for bosons is the following. When you try to fix the number of particles and find the chemical potential as a function of temperature that gives you that number of particles, you might have situations, so this chemical potential as a function of temperature is negative, 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 but you might have unlucky situations, not unlucky, very lucky situations, but peculiar situations, in which this chemical potential at some point hits 0. Now, in principle, we would say, when it hits 0, then I continue at lower temperatures, it becomes positive, but this is nonsense. It can't be positive. So what is happening when the chemical potential from negative hits zero is that you have a so-called Bose-Einstein condensation transition. From this critical temperature on, you will get that a macroscopic fraction of your particles will occupy the ground state of your system, and all the others will be sitting in excited states. Okay? So this is what we are going to discuss next time, Bose-Einstein condensation, and then we are going to do a few exercises on Bose-Einstein condensation for a few lectures, for one lecture. Okay? And then we are going to proceed with other quantum mechanical stuff. Okay? Questions? I see you very unhappy. Don't worry. Yes. Well, it has to be complicated, right? Let me see what I did last year. Subject. To do one of the, I mean, we're a bit, I'm not saying we're done with the course, but we can use one lecture for practicing the exam. Would you like to do it?
Yes.
Okay. When shall we do that? When do you think you will be ready for a real practice?
Will it be like a practice exam or?
Practice exam means I'll give you one of the exams of the previous years.
And we do it here.
And you do it here.
Okay.
Well, perhaps one less exercise.
Next month.
Maybe after 25th of November.
I think
Just
after
after
29.
What, 29th?
What is
Oh,
I think in December
Yeah.
will be
yeah, maybe in December will be better.
Okay,
Yeah.
so we do it on sometimes the first week of December.
Yes.
Second
No,
week I'm
first-
finished teaching.
First week, yes.
I mean, I can
Before
do it
14th.
first week of the 2nd of December. So, and then my last lecture is the 11th of December. So shall we do it? We can have one lecture doing that. Maybe we take more than. Yeah, I will see if they can give us half an hour more, right? And then we do it for 2 hours. Would that be okay?
Yes.
This way you practice before the final exam.
Can you tell me a little bit about adiabatic demagnetization?
Adiabatic demagnetization.
Yes. Refrigeration.
Well, I mean, it's, I don't really know what you mean, but I suspect that it's simply when you take a.
It's a mechanism to reach the Kelvin temperature. Then they have magnetic ferromagnet material, and then you kind of remove the you apply magnetic field, and then you remove the magnetic field, and their entropy increases and then that they
Okay,
start
I
with
have to
temperature.
study that. So if you want, I can study it, and then I can answer your question. And now I would have to invent an answer.
Okay,
What could probably be not the answer to your question.
okay, okay.
So I am not really familiar with it.
Can I set a time to come to your second
Yeah,
class?
well, let's do it next week. So let me write it down. Let's do it next week before the lecture. So, just a second.
Maybe we can just look this out.
So next week we have a lecture. Let's do it at 10:30 next week. It's on Wednesday in my office upstairs. Just a second. I'll be back. Now I'll try to figure out this. Okay.
Yes, I have class in the morning, so I'll just come after the class. And
What time is your class?
it ends at 10:30.
Oh, okay, so then it's perfect. Okay, good.
That? Or you?